Hey, how's everybody doing? Welcome back to our Math for Healthcare video lecture series. Today we're going to jump into probability distributions of random variables. Alright, so we're going to be using what we learned previously to understand these probability distributions rather than just single probabilities. Okay, so first of all, we need the idea of a random variable. So a random variable is a rule that assigns a number to each outcome of a chance experiment. For instance, we may say, okay, let the random variable x be the number of heads when tossing 10 coins. Okay, so something like that. That's what I mean by an assignment that assigns a number to each outcome. And let's more specifically look at what we have here. Let's consider tossing a coin 3 times and observing the number of heads. Let the random variable x denote the number of heads that occur in 3 tosses. Now, if you recall from the last video, we said, well, we're tossing coins. We got independent trials. We have either it's a heads or not a heads, so only 2 outcomes, success and failure. So that we have a binomial, right? Those were binomial probabilities before. That's just to remind you. We'll go over that more as we move forward, okay? Now, recall we got the sample space. We know what that is, right? And now we know how we could count this in general, right? If we were, say, tossing 10 coins or something like that. This is so we could break it up and see everything. What do I mean by assigning? So head, 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 that gets set a value of 3. All right. Heads, heads, tails gets a value of 2. But so does heads, tails, heads, and tails, heads, heads. Okay. And similarly for the rest of them, the ones and the zeros. Okay. Now, notice we could only have 0, 1, 2, or 3 heads. The set 0, 1, 2, 3, that's the range of x. What are the values it could take on? Those are something that you're going to want to look at once you define your random variable. All right, so here, the event that exactly 2 heads come up, we write that event as x equal to 2. That is the same thing as writing this curly brackets, HHT, HTH, THH, right? Those are events. They are the same thing. So when a random variable takes on a value, it represents an event. Right? And so here we could find the probability of that, right? The probability of x equal to 2 is 3/8. Again, that would be the same thing as the probability of if we set this event over here, and let's say that's E, right? That's going to say that's equal to the probability of E. Okay. Now, likewise, the event 0, where x is greater than or equal to 0 and less than or equal to 1, that has, okay, so anything what is 0 or 1 in this case, because you can't be in between, right? So all tails, head, tail, tails, and so on. Our event here, maybe let's say that we'll call that event F, right? And of course, similarly, now we could find the probability of that, right? And then we just had a count. We go up to our sample space and we count how many of them. There was 4, right? Or while our event 2, or event F has 4 in it, we know the sample space says size 8. And so the probability of our random variable being between 0 and 1 inclusive is 4/8, otherwise known as 1/2. All right, so again, what is it? Those things are the same. This and this, they are the same. Same, but written differently. And we could see this is going to be very convenient notation with a random variable in order to move forward with our studies. All right, so let's find an example. Okay, suppose we have the experiment where a coin is tossed 3 times and we have the following sample space. Well, we saw that, right? Let's say y be the random variable that is the number of tails observed. What is the event y equal to 1? And what is the probability of y equal to 1? Well, in this case, y equal 1 is the event, let's see here, what do we have with the number of tails observed? Heads, heads, tails, heads, tails, heads, and tails, heads, heads. All right, that's the event. And the probability that y equals 1 is then 3/8. We've seen this before. We know this already, right? Good. Okay. Now, so we have these random variables. Now, where does the probability distributions come in? All right, so we learned already the probability distribution for an experiment. We have each outcome is assigned a probability between 0 and 1, inclusive, and the sum of the probabilities of the outcomes has to be 1, right? We saw that in the last section. So now we wanted to find the probability distribution of a random variable, which is somewhat, to say, the adult way to do this. This is how you're going to see it if you go on to statistics, and if you read any papers, that's always going to be, it'll be in this language here. All right, so what do we have to do? Well, it's really the same thing, right? Except for we're doing it for the different x values, all right? So in this case, if a random variable x assumes some values, x1, x2, xn, so those x1s through xn, those are a range of our random variable x, then the probability distribution of the random variable is an assignment of a probability to each value, which can be expressed in a table like this. All right? So first of all, over here, this is the general, and maybe I should write a line here. That's kind of different. We don't plug in numbers on that left side. That tells me my values, my x values, and if you want, you could put in big X equals xi, whichever you want. My random variable values, okay, are in the top, and my probabilities are in the bottom for the appropriate value of x. So, for instance, what do I get here? In this first one, we get x1, all right, whatever value it is, and then underneath it is the probability of xn, and so on out to xn. And of course, like we said, it satisfies the following two conditions. All probabilities have to be between 0 and 1 inclusive, and when I sum them up, they have to be exactly 1, not close, exactly 1. This is part of being a probability distribution. All right? Now, so for our example, where we flip a coin 3 times, we already discussed a range is going to be 0, 1, 2, or 3. In other words, x1 equals 0, x2 equals 1, x3 equals 2, x4 equals 3. All right? And now you don't have to write all those out. We simply write the values that it takes on. Remember, that was the range. All the numbers in the range of our random variable x goes on the top. And then we put in the appropriate values for our probabilities, right? The probability of getting 0 heads is 1/8. The probability of getting 1 head is 3/8, and so on and so forth. And you could check for yourself. Obviously, those are all between 0 and 1, and if you add them together, we end up with exactly 1. Now, one thing to note here is, if A is an event that 3 heads were observed, we could write the probability of A equals 1/8. And really, the event A is equal to, what is it? The event that we get 3 heads observed is the event X equal to 3. Right? But that means that when we look at the probabilities, right, we have to plug in that whole x equal to 3 term here for this. So if x is a random variable, the expression p of x here, it's meaningless. And so just be careful with that. We need the value in order to know what the event is. And it's a little different. We're not just plugging in a letter like we did with our events before. All right? The input into the probability function must be an event. All right, x by itself, that's a random variable. It's not an event itself. Now, one thing with probability distribution of random variables, we could look at it graphically, and when we have discrete random variables, it's going to be a histogram, and over here on this side, and this is what it would look like. And if you notice the block, if you consider each block being a width of 1, you added up that shaded region, the area is 1. In general, there's usually always this. We think of probability as areas under some curve. And yes, this is right angles, but technically it's a curve. Okay? And the area underneath it equals 1, and that makes it a probability distribution. Okay. So here, I'll let you read through this pretty lot. I think it's pretty self-explanatory, but the slides are available. You can look at if you want to make yourself a histogram. I think you could see from the picture how we're going to do it. We just, like I said, each bin we make a width of 1, and so 0 goes up to 1/8 because the probability of 0 heads is 1/8. I do want to take a look quickly in Desmos here. So notice up here, I put in, So up my top table there that I just made visible, I put in the probability distribution, right? I mean, I get it that it's vertical instead of horizontal, but it means the same thing. In fact, you could write it either vertical or horizontal. And here I'm represent x1. What do I mean by that? Those are my values for my random variable x, and then y, I put in the probabilities. Now you're not going to get the nice boxes, but it does give you the probability distribution. Don't forget using that magnifying glass to get in on the data here. And here, notice we could think about that as, just imagine these with 1 blocks, and that gives you an idea. Hopefully you see the similarity to the shape in what was drawn by hand. Because a lot of times you're just not going to be able to draw it by hand. We need a machine to do it. Okay. Now, let's say I wanted to compute probability of x being between 1 and 2. Okay, I think we know from our last few slides we could figure that out. Go ahead and calculate it. And that's going to be 3/8 plus 3/8, right? Because that's the probability here. It's either 1 or 2, and that's going to be 6/8 or 3/4 or 0.75, whichever you prefer. All right, now in the histogram, what are we doing is we just add up, just like we did, add up those probabilities, and you could think of that event as, what is it? The area of this blue shaded region is 6/8 or 3/4. And here's another nice picture of it. Same thing as we just drew shaded up top. That's our relationship between probability and area. Okay, so let's see here. How about this example? Does the following histogram depict a valid probability distribution for a random variable? Why or why not? Hit pause and go ahead, and you should be able to answer this on your own at this point in time. Now, okay, so let's see here. Are all the probabilities between 0 and 1? Yes, that is true. Okay. Now let's see. What's the other thing we got to check? Oh, yeah, they got to add to 1 exactly. Let's see here. No, when we add up those probabilities, 1/8 plus 4/8 plus 3/8 plus 3/8, we get 11/8. That's not equal to 1 as required, so this is not a valid probability distribution. All right, let's see here. Last example is, so let's say we got a group of 100 students. We ask to rate their math class on a scale from 1 to 5, 5 being the best. The following responses were obtained. We're going to let the random variable x denote the rating given to the math class by a random student. Okay? So here, notice again, I'm always defining that random variable, just like we did in the linear part of the class. We wanted to, where we defined our x and y values in a problem for linear regression and those sorts of things. And you really need to do it for your random variables as well. It'll keep you on track. They're very useful tools, but you need to define them from the beginning. You need something to look back on for it. All right. All right, so here we want to find the probability distribution associated with this. Now, let's see here. First of all, what's the range of x? A random variable x is what? You could either get a 1, a 2, a 3, a 4, or a 5. There's no in-betweens, right? So that's the range of x. So we go and do our probability distribution. All right, what are the values that I could take on, and what are those probabilities? All right, we get 1, 2, 3, 4, and 5. Now notice here, they didn't give us probabilities. They gave us a frequency distribution. All right, but so what do we do with that frequency distribution? We put, so what percentage of people gave a rating of 1? 15 divided by the total, which is 100. All right, so that's nice and easy for our calculations. We could have probability of x equal to 1 is 0.15, 15%. Probability of x equal to 2, carefully, this is what? 0.0505, right? And 0.1, the probability of a 3. Probability of a 4 is 0.36, and a 5 is 0.34. All those are between 0 and 1. We add them up, and we get 1 exactly. All right? Now, let's see here. By the way, let's look at, before we answer the next question. So that's our probability distribution, right? How can we look? We could look in Desmos. All right, let's get rid of the ones that we had for this problem. Notice I just put in our probabilities for the appropriate values of x, and you may want to use this to get it in. And now, so this one looks a little bit different, right? So the first one is it's got the high. It's not symmetric, right? Well, let's see here. Let's go. If we looked at the green alone, okay, the coins, notice like it's the same on either side, right? They even each other out. The blue, which is these kids, no, it's heavy on the high side, okay? So that's our probability distribution, and that's how we could visualize it in Desmos. Now, what did it say here? What is the probability that the randomly chosen student rated the math class at least a 3? Okay, so we're looking for probability that x is greater than or equal to 3, which is the probability that x equals 3, which is 0.1, plus the probability that x is 4, which is 0.36, plus the probability that it's 5. And because of the shape of it, we're not going to be surprised here. We end up with, let's see, 0.6, 0.7, 0.8, or 80% chance of a 3 or greater, right? In other words, the area under that curve is 0.8 from 3 up. Good. So 80% chance. All right. Let me know if you have any questions. Go ahead and try some homework, and I'll see you in the next video.